Here we go. Today we are talking about energy. This is section 13.3, and we have got three objectives that we're going to cover today. One, to explain the relationship between energy and work. Two, to define and calculate potential and kinetic energy. And three, to identify and distinguish between various forms of mechanical and non-mechanical energy. So let's get going here, starting with energy. Now, the cool thing about energy and work, they have a lot in common, right? The first thing that these things have in common is that they're both measured in joules. Okay, energy is the ability to do work. And if you think about it, like if I want to do work, it's going to require energy, right? Well, the one thing that they have that is not in common is that one of them requires a motion to be in place and the other doesn't. So for instance, although they're both measured in joules, it's only work that requires the motion, okay? So you have to have motion in order for work to take place, but you do not have to have the motion for energy. So energy can take place without motion, but work cannot. So I can be pushing against the wall for a long time, right? And I could be like exerting a ton of energy, but it will do no work according to the scientific definition because that wall hasn't moved any, at least no work on the wall. And so that's the big difference, is that work requires energy and work requires movement, but energy does not require movement. And so they're both measured in joules. So they have some similarities, but they have a little bit of difference. But it's cool to see that they're related in that way. Now, we have two basic types of energy that we're going to talk about right now, and these are potential versus kinetic energy. Now, if you look at this value here, if this is the ground down here, then we have a little bit of space between the bottom of the ball and where the ground is. So this has a very low potential energy. Potential energy is based upon position, okay? Potential energy is based upon position. If I had that sphere up here a little bit higher, okay, then I would see that I've got a difference in the position, right? So from here to here is the change that it would be going through from going from the bottom to the top. And so you have a change in position here, so you have a change in potential energy. So the potential energy is based upon position, and we're going to show you a formula here in just a second that will we'll kind of go into that into a little bit more detail. But when we're on the ground, all right, if we had the sphere here on the ground, then if we have to describe our height, we would describe our height as 0, right? Like maybe we're 0 meters high from whatever our point of origin is. So we'd have to describe our potential energy as 0. Now, the reason for that is because of our formula. If you look here at the formula is mgh. So if my height is equal to 0, then this whole thing is going to be something times 0, which means potential energy would be 0. Okay, so potential energy is based upon position, and you've got to have some sort of height in order to have that position. And so that's why you've got to imagine the potential energy based upon location. Okay, so our units for potential energy, joules, just like in work. Okay, now it's kind of cool to think about the units here, right? And if you guys just to kind of take a little reminder, work was equal to force times distance, which was a Newton meter, if you guys remember that. And if you remember, a Newton, force is equal to mass times acceleration. So a Newton was a kilogram times a meter per second squared, right? So a kilogram meters per second squared times a meter is basically what we've got. So this is our unit, kilogram meter squared per second squared. That's joules. And we can see that that's going to happen here with potential energy as well, right? So if we look at our mass, that's kilograms. We look at our free fall acceleration, that's 9.80 meters per second squared. And we look at our height, that's meters. So let's put those together. mgh, right? So I've got my meters, my mass, and that's going to be kilograms. And then I've got my free fall acceleration, which is meters per second squared. And then I've got my height, which is in meters. So look what I've got, the same thing that I had down here, right? These are equal to each other. Two different ways to come up with the same units and the same energy. One of them has to do with moving a force through a distance. The other one is taking and looking at the position of an object, you know, relative to the ground. And you get the same units, okay? And you can actually kind of think of potential energy, you know, and work in the terms of force right? Because if I have ma, that's mass times acceleration due to gravity, then I've got a force times a distance, right, times my height. My height is kind of like my distance, and my mg is basically my weight. So it also works like that. All right, so let's look at a practice problem and see how we do on this one. All right, so we've got to show our work as we're doing our problems, right? We've got to make sure that we show our work. And the way that I score points, each of these types of problems were 5 points. And the first part of your point, the first point that you would get would be based upon your givens. So you got to show your givens. So I've got to say my mass is equal to my number of kilograms, right? So it's 65 kilograms. And then my height is equal to 35 meters. And then we've got a G that we know we've memorized is 9.80 meters per second squared. And then it says that we're looking for our potential energy, right? So we've got our mass, we've got our height, and then it says we're looking for potential energy. And so PE equals question mark number of joules. Now this is what you'd have for given. You need all of that in order to get the 1 point for given. And that includes your units, right? Then we put down our formula. PE is equal to mgh. That's 1 point. Then we have to say, do I need to manipulate this formula, solve for mg or h? In this case, no. We don't need to do that because we're solving for PE. And so we just have to say, all right, I get my free manipulation point. I don't really have to do manipulation. I've just got to now plug it in. So PE is equal to the mass. So I say 65 kilograms, right? And then I say times my acceleration due to gravity, 9.80 meters per second squared, and then times my height, which is 35 meters. Then I get my answer, right? I multiply those together, and you're going to get an answer of 22,295 joules. But my last step is to finalize this, right? Part of my solve is to make sure I have the right number of sig figs. And if you'll notice the original problem, okay, we had 2 sig figs. Okay, get rid of some of that stuff there. We had 2 sig figs here with our 65, and we had 2 sig figs with our 35. So our final answer also has to be expressed in 2 sig figs. So we box that 22,000 joules as our final answer. Okay, so that's how you would solve a potential energy problem. Now let's look at kinetic energy. Kinetic energy has to do with velocity. Okay, now you need to see these 2 cars. Let's assume these 2 cars are identical in mass. So what that would mean is that we can determine their kinetic energy based upon their motion. All right, so identical mass is going to be the same, but they don't have the same speed. This one is moving faster, right? And so if you have 2 identical objects in terms of mass and one of them is moving faster, then you're going to end up having a greater kinetic energy with the one that is moving faster. All right, so kinetic energy has to do with the speed of objects or the velocity of objects. So here's the formula for it. Okay, KE is equal to 1/2 mv squared. Kinetic energy, again, our units are joules. It's energy due to motion. Our mass is still in kilograms. Our velocity, remember, our unit is meters per second. So if we look at how that pans out, we can see those same units. If we take our mass, that's kilograms, and we take our meters per second and we square it, then we end up getting a kilogram meters squared per second squared. And this is exactly what we saw before with our potential energy in our work. We end up with joules. So it's just fun to be able to see that you can have 3 different approaches to coming up with the same unit. One that describes the energy of, with regard to motion, another one which describes, work, and another one which describes energy due to position. It's fun to see that you get the same things. So let's see how we would solve this problem. What is the kinetic energy of a 44 kilogram Jaguar running at 31 meters per second? So again, we've got to follow our procedure, right? Let's write down our givens. So KE is question mark number of joules. That's the first thing that they're saying we need to look for. 44 kilograms, that's mass. 31 meters per second That's velocity, right? Now, it would be nice if we actually had a direction in this case to actually call it velocity, but we can just go with this for now. Then we've got to say, all right, well, let's solve it with our formula. Which formula are we using? Well, KE is equal to 1/2 mv squared. All right, well, let me substitute then. I don't have to rearrange. I don't have to manipulate because I'm looking for KE, and I've got KE as my original formula. So I just have to say, all right, well, KE is equal to 1/2. You plug in the mass, 44 kilograms, and then you plug in the speed or the velocity, 31 meters per second. Very important that you put this in parentheses, and then you put the square on the outside of that parentheses so that you know that it's squared. Okay. And so once you do that, and you take 31, and if you guys haven't used your calculators in a while for something like this, what I would suggest is when you have something that's like a squared, you do that first. Then you don't have to worry about the parentheses. So you can say 31, and then you just hit that square button, and then multiply it times 44, and then divide it by 2, and you get your answer. And so your answer would be 21,142 joules. But we can only have 2 sig figs, right? Because 2 sig figs for each of those originals. So we do our final answer as 21,000 joules. You could also, if you wanted to, you could also do, that's a funny looking J. You could also do 2.1 times 10 to the 4th joules. And that would be a good answer as well. But make sure you box it, finalize that problem. Okay, so that's how you do those kinetic energy problems. So what we're going to do now is we're going to take a moment and we're going to let you try one of these kinetic energy problems. And then we're going to see what you get. There's a lot of them on page 448, but I want you guys to try this one. Okay, so I'm going to take a moment and I'll let you guys practice this, and then we'll come back in a little bit and see how you've done. Givens, right? So we want to start with our mass of 60.0 kilograms, our velocity of 4.0 meters per second. And then it says we're looking for KE, right? Kinetic energy. And so we have to say question mark number of joules. Now, what we're going to do is we're going to take that and we're going to say, what's our next step? And again, this is that whole first step was 1 point. So if you didn't do that first step, then you would have missed a point out of the 5. And then you say, okay, well, my next step is my formula, 1/2 mv squared. That's another point out of the 5. You don't have to manipulate. You're solving for KE, and so you're good to go there. So all you have to do is now plug it in, right? So you substitute. And so you say 1/2 the mass. So I go 60.0 kg. And then times my velocity squared, right? So 4.0 meters per second. Again, that square needs to be on the outside of that, right? So you plug it into your calculator, you do your 4 squared, right? We all know that's 16, and then we multiply that times 60, and then we divide by 2. So you get that 480. So kinetic energy is equal to 480 joules. Now, you have 2 sig figs here, 3 sig figs here. Your final answer with multiplication problems has to be in the same number as your least in your original part of the problem, and so that's 4.0. So my final answer should have 2 sig figs, which this one does, and so that's how you'd finish that one out. I'll make sure you box that to get your final answer prepped. Okay, so now you know how to solve kinetic energy problems. Now let's talk about mechanical energy versus non-mechanical energy. Mechanical energy is the total amount of work that an object can do based upon its kinetic and potential energies. Okay, so you kind of want to think of KE plus PE, right? It's kind of like the sum of the kinetic and the potential energies. Okay, what work could I do if you had some sort of a cliff here, and you were having a ball drop off the cliff, right? And let's say the ball is like right here, and so it's kind of in the middle, and it's falling. It's got some kinetic energy because it's moving. It's also got some potential energy because it still has the potential to go down even further, right? And so if this ball were to do work of some sort, okay, then it is going to have the ability to do work based upon its kinetic energy and its potential energies. And so mechanical energy is that overall amount of work that an object can do because of that. Now, when I say mechanical energy, and I talk about these two types of energies, one of the things that we want to focus in on, believe it or not, even though we haven't said it yet, is it's something that we can see. And, it's just like when I say, hey, what's non-mechanical energy? You need to be thinking about stuff that we don't really view with our eyes. Okay, so mechanical energy are things that, we can see. It's able to do work, and it's something kind of like in the macroscopic, the larger types of object. If we go down to the size of atoms, we talk about the motion of atoms. Well, motion is kinetic energy, right? And so if I have motion of atoms, that's still kinetic energy, but it's not stuff that we can see, right? And so if it's down to the size of atoms, we call it non-mechanical energy. So there's some small stuff is the stuff of atoms, right? The big stuff, the stuff that we can see, that's part of mechanical energy. But the stuff that's really small, we're going to call it non-mechanical energy. Even though, yes, the things are still in motion. Yes, for instance, like chemical energy, you have stored potential energy in chemical bonds, right? But that kind of stuff we're going to all call non-mechanical energy. The stuff we can't see that still has energy, we're going to be talking about that as non-mechanical. But the stuff we can see, like a machine, an object falling, or doing work with things like that, that stuff is going to be mechanical energy, okay? All right, so that's mechanical energy. Let's look at some of the non-mechanical energy types, okay? Down at the levels of the atoms, we want to think about the fact that these are special types of kinetic or potential energy, right? Non-mechanical forms are just going to be special. They're still kinetic energy. They're still potential energy. They're just special, okay? Not the stuff that you'll look at and see. It's going to be much smaller stuff. Time to wake up from my nap. All right, so now we go on to non-mechanical forms of energy types. Let's look at some of them. Chemical energy, right? Chemical energy that you might see in a chemical reaction is a form of non-mechanical energy. Now remember that when bonds form, that the reason that bonds are forming is to reach lower potential energy. So if we were thinking about, two separate carbons on the top of a cliff, by the time they got down to the bottom of the cliff, they would have formed a bond. And they have released potential energy as they did so, okay? So as they fell down, they kind of released their energy. Whee! And they came down to a lower potential energy state. So just remember that when you are forming bonds, you're releasing energy, okay? When you're breaking bonds, then you're going to be absorbing energy. It requires energy to do that. And so chemical energy is a form of non-mechanical energy. Light, okay, is going to be a part of non-mechanical energy. But here we're still talking about chemical energy, really, because we're still talking about photosynthesis. But we have the energy in the sunlight, which is a non-mechanical energy. And then that's going to be turned into chemicals, right? We also have energy from the sun, which again has to do with non-mechanical energy, right? It's light, but we can get that from nuclear reactions. So nuclear reactions, that nuclear energy is going to be a form of non-mechanical energy, okay? We have it in the form of fission and fusion, right? Fusion is what we have inside the sun. That's what's in the core of the sun, which is giving us all this energy. We also have fission, which we see here on Earth a lot more, right? And then that's another form of non-mechanical energy. We also have energy stored in fields, like electric fields, okay? So when we think about energy of electricity, okay, we want to think about electricity being non-mechanical energy, okay? Now, electrons will move from one place to the next. We call it electricity, right? And where are they moving from and to? Well, they're always going to move from higher potential to lower potential. And so that is what we see happening here. But the idea here is that, we have non-mechanical energy. That in order for an electron to go from this, higher potential to this lower potential, it's going to gain energy, right? But the idea, again, is this is a form of non-mechanical energy. Not super important that you understand how that works. Just note that electricity is non-mechanical, even though it has to do with the movement of electrons, right? All right, so light is another form of non-mechanical energy, right? We see that it's a form that can actually travel across the vacuum of space, right? But it's light. Light is a form of non-mechanical energy, and it comes in forms of varying degrees, right? We have things from gamma rays all the way to radio waves that are all considered electromagnetic waves, all considered types of light, basically, right? And so electromagnetic waves or light is a form of non-mechanical energy. And remember that involved with that is magnetic fields, right? So magnets, although a magnet might have some mechanical energy to it as it falls, the field that it creates would be non-mechanical, okay, energy that it could actually use to do something. All right, so that's non-mechanical. So we've got a bunch of different types of non-mechanical energy forms. All right, so that pretty much covers everything in chapter 13.3. Let's go over what we've learned. What's the relationship between work and energy? Remember, energy is the ability to do work, and that they both are measured in joules, but you have to have motion for work to take place, and you don't have to have motion for energy to take place. Remember that potential energy is determined by position and mass. Kinetic energy is determined by the velocity and the mass, okay? And then non-mechanical energy, all sorts of this types of energy that are going to be really from the small stuff, right? The size of atoms, but it has to do with light, okay? We just went through a bunch of them, right? So like light, electricity, we have magnetism, we had nuclear, okay? We had chemical, all sorts of non-mechanical energy. So all stuff that's really small, and it's still energy, but it's a special type of kinetic and potential energy. All right, so that's all we're going to talk about today. I hope you guys enjoyed the lecture and have a great rest of your day.